talk a little bit about the Coriolis effect, which people say that that's why toilets, the water in the toilet spins in a certain direction. By the way, the water in my toilet doesn't spin; it just goes straight. But that this is a myth. The manufacturers of toilets put the nozzles in a particular direction to make it spin. Okay, but storms and things like that actually do spin because of the Coriolis effect. We can notice the Coriolis effect if we ride the carousel at Oaks Park. I've done this. Okay, in a rotating system, what is lost on the people in that rotating system is if I'm, say, sitting on an inside horse and you're sitting on an outside horse, is that you're actually going faster. Your tangential velocity is bigger, and that's because your tangential velocity is omega times r. We both have the same omega, but you've got a bigger r, so you're going faster. Okay, if I throw a ball straight out at you, okay, I'm throwing it to a region on this thing where the velocity is faster to the left. Okay, and so the ball tends to, in that frame of reference, seem to curve off behind that person. And it's very real. If you try that, just honest to God, try that. This is one of the exciting things we'll do at Oaks Park. Okay, just try it. Throw a thing like that, and you can actually see it's got a wicked curve like that. And if B throws it this way, they're throwing it to a place where it's going slower, right? So it tends to curve like that, which means that air masses that are converging on a center won't meet head on, and they'll tend to actually, I guess, spin anti-clockwise or something like that. Okay, so on the carousel, we can definitely see the Coriolis effect. At OMSI, they once had a carnival ride exhibit, which I wish would come back, and it was this rapidly spinning room, and it was possible to throw the ball to yourself. You'd throw it straight across, and it was rotating fast enough that by the time it reached the other side, you were there to catch it. Now, it didn't look like it was going straight at all to you. To you, it looked like it was curving, this wild, crazy thing coming around. But as this thing just went around, you'd release it here. By the time it reached the other side, you'd be here, and you'd catch it. And it was the weirdest thing. It was the strangest illusion. It also was very dizzifying to be in this rotating room. Okay. And then the final thing I'll let you do before you watch the Very Fine Khan Academy video, okay, is to just consider that the Earth is actually a rotating frame of reference, right? And so if you're on a spot in the Earth, if you're here and you are maybe launching something this way, okay, you're launching it to a place that is going slower to the east. Everything goes to the east, right? Okay, it's going slower to the east, and so things are going to tend to curve this way. And if I launch it this way, it's going to tend to curve that way. During World War II, the battleships that fired shells, right? These shells are unguided. Once they go into the air, they just go more or less straight, right? And the Earth rotates, right? And they had to take into account the Coriolis effect to hit a target that was maybe 30 miles away or something like that. Anyway, watch the video that is from the Khan Academy, and that explains why storms rotate anti-clockwise in the northern hemisphere and clockwise in the southern hemisphere. Anyway, enjoy.